Arc flash hazards pose a significant risk in electrical systems, and understanding them is crucial for ensuring workplace safety and preventing equipment damage. An arc flash is a type of electrical explosion or discharge that occurs when a fault current flows through the air between conductors or between a conductor and ground. This can result in extremely high temperatures, intense light, pressure waves, and toxic gases, all of which can cause severe burns, injuries, and even fatalities. Arc fault analysis is a systematic process of identifying, evaluating, and mitigating arc flash hazards in electrical systems. It involves determining the potential incident energy levels at various points in the system, assessing the risk to personnel, and implementing appropriate protective measures. Firstly, understanding the types of arc faults is essential for effective analysis. There are primarily two types of arc faults: bolted faults and open air or arcing faults. Bolted faults involve a direct short circuit between conductors, typically resulting in high fault currents and significant energy release. Open air or arcing faults, on the other hand, occur when the current flows through the air, creating an arc. These faults can be more difficult to detect and interrupt due to the lower fault currents involved. Secondly, arc flash protection methods play a critical role in mitigating the hazards associated with arc flashes. These methods can be broadly categorized into passive and active protection strategies. Passive protection methods focus on minimizing the likelihood of an arc flash event or reducing its severity. Examples include proper insulation, separation of conductors, and the use of arc-resistant equipment. Active protection methods, on the other hand, aim to quickly detect and interrupt an arc flash event, limiting the duration and energy release. These methods typically involve the use of protective relays, current-limiting devices, and arc flash detection systems. Thirdly, arc flash analysis techniques provide the means to quantify the potential hazards and determine the appropriate protective measures. These techniques typically involve the use of software tools to model the electrical system and simulate arc flash scenarios. The analysis takes into account factors such as the system voltage, fault current, clearing time of protective devices, and the distance from the arc flash source to personnel. The results of the analysis are used to determine the incident energy levels, arc flash boundaries, and the required personal protective equipment or PPE for workers in the vicinity of energized equipment. When performing an arc flash analysis, several key factors need to be considered. Firstly, the electrical system model must accurately represent the system configuration, including all relevant components such as transformers, generators, cables, and protective devices. The model should also include the impedance values of these components, as these values significantly impact the fault current levels. Secondly, the fault current calculations must be performed accurately to determine the maximum available fault current at each point in the system. This involves considering the source impedance, transformer impedances, and cable impedances. The fault current calculation should also take into account the contribution of motors and generators to the fault current. Thirdly, the clearing time of protective devices is a critical factor in determining the incident energy levels. The clearing time is the time it takes for the protective device, such as the circuit breaker or fuse, to interrupt the fault current. The faster the clearing time, the lower the incident energy. Therefore, it is essential to select and coordinate protective devices to minimize clearing times while maintaining system reliability. Fourthly, the working distance is the distance from the potential arc flash source to the worker's body. The incident energy decreases rapidly with increasing distance, so the working distance significantly impacts the required PPE level. It is essential to establish safe working distances and ensure that workers maintain these distances when working on or near energized equipment. Fifthly, personal protective equipment, or PPE, is the last line of defense against arc flash hazards. PPE includes items such as arc-rated clothing, face shields, helmets, gloves, and footwear. The PPE must be selected based on the incident energy levels calculated in the arc flash analysis. It is crucial to ensure that workers are properly trained in the use and maintenance of PPE. Example calculations and case studies can provide valuable insights into the practical application of arc flash analysis techniques. These examples can demonstrate how to perform fault current calculations, determine incident energy levels, and select appropriate PPE. They can also illustrate the effectiveness of different arc flash protection methods in reducing the risk of arc flash injuries. One common example involves performing an arc flash analysis on a 480 volts motor control center. The analysis would typically involve creating an electrical system model of the motor control center, performing fault current calculations at each bus, determining the clearing times of the circuit breakers, and calculating the incident energy levels at each location. Based on the incident energy levels, the appropriate PPE would be selected for workers performing maintenance on the motor control center. Another example involves evaluating the effectiveness of different arc flash protection methods in reducing the incident energy levels. For instance, the analysis could compare the incident energy levels with and without the use of current limiting devices or arc flash relays. The results of the analysis can help determine the most cost-effective and practical protection methods for a given electrical system. Complying with industry standards and regulations is essential for ensuring electrical safety and mitigating arc flash hazards. Several standards and regulations provide guidance on arc flash safety, including the National Electrical Code or NEC, the National Fire Protection Association or NFPA 70E, and the Institute of Electrical and Electronics Engineers or IEE 1584. The NEC provides requirements for electrical installations, including requirements for arc flash hazard assessments and labeling. NFPA 70E provides guidance on safe work practices for electrical workers, including requirements for arc flash hazard assessments, PPE, and training. IEE 1584 provides equations and methods for calculating arc flash incident energy. Optimizing electrical system design and maintenance is another important aspect of arc flash hazard mitigation. Proper system design can help minimize the likelihood of arc flash events and reduce their severity. This includes selecting appropriate overcurrent protection devices, providing adequate insulation and separation of conductors, and using arc-resistant equipment. Regular maintenance and testing of electrical equipment are also essential for identifying and correcting potential problems before they lead to arc flash events. This includes inspecting and testing circuit breakers, transformers, cables, and other electrical components. By understanding and mitigating arc flash hazards, facilities can significantly improve safety, comply with industry standards and regulations, reduce downtime and equipment damage, and optimize electrical system design and maintenance for increased reliability. A proactive approach to arc flash safety is essential for protecting workers and ensuring the safe operation of electrical systems. Electrical engineers, facility managers, safety professionals, and anyone involved in electrical system design, operation, or maintenance should use this guide to enhance electrical safety at their facility. Reducing downtime and equipment damage caused by arc faults is another important benefit of implementing effective arc flash protection measures. Arc flash events can cause significant damage to electrical equipment, leading to costly repairs and extended downtime. By mitigating arc flash hazards, facilities can minimize the risk of equipment damage and reduce the associated downtime. Improving safety by understanding and mitigating arc flash hazards is the primary goal of arc flash analysis and protection. Arc flash events can result in severe burns, injuries, and fatalities. By understanding the hazards and implementing appropriate protective measures, facilities can significantly reduce the risk of these events and protect their workers.